I was recently talking to a venture capitalist who was bragging about his portfolio's compute moat. He was scrolling through photos of a massive server farm. His latest startup had just leased rows of gleaming Nvidia H100s, still smelling of the factory floor and fresh capital. He looked at those racks the way a medieval king might look at a wall of hired mercenaries. To him, this was the peak of the AI arms race. "We're buying every chip we can get our hands on," he told me, his eyes wide with that frantic energy you only see during a gold rush. "If you have the silicon, you have the soul of the future." But then I asked him a simple question. What happens when the owner of the land decides he wants the crop? His expression shifted instantly. The excitement didn't just fade, it curdled. He started complaining about lead times, the Nvidia tax, and the sheer entropic cost of translating code across layers of proprietary middleware just to get a single inference. He realized in that moment that he wasn't building a god. He was just a tenant farmer on someone else's digital soil. He was paying a premium for the privilege of working within a patchwork architecture that wastes energy with every instruction. That conversation stayed with me because it highlights the invisible wall the industry is about to hit. While the world's most famous AI labs are busy buying sand and haggling over GPU allocations, a much quieter, more clinical transformation is taking place. It is a shift from assembly to alchemy, a move towards sovereign compute. It's the difference between those who are governed by the volatile laws of the market and those who are beginning to dictate the fundamental laws of thermodynamics. We're entering an era where the gap between those who lease their intelligence and those who manufacture its very physics is becoming a civilizational chasm.
That is such a powerful way to frame it. The tenant farmer versus the sovereign builder. It really gets to the heart of the economic and, frankly, the physical reality that we need to dig into today.
Exactly. And that's our mission for this deep dive, right?
Yeah.
To really understand this fundamental shift that's happening in AI infrastructure.
It's about moving away from relying on, these fragmented third-party pieces of silicon.
And toward what? These vertically integrated systems, this idea of sovereign compute.
Yes, where your guiding principles are the laws of physics, not just the whims of the market.
Okay, so we're going to cover the strategy behind it, the sheer economic force of it.
And how it all connects back to the core physical limits of what computation even is. We're really defining this new chasm, this dividing line between the owners of the stack and, well, the renters.
And this is so much more than just who has the faster chip. It's about architectural integrity, it's about cost, and as you said, the thermodynamic destiny of intelligence.
It really is.
So let's start with the architecture itself. Because the whole idea of what a core unit of computing power is, that's completely changed, hasn't it?
It's been a massive evolution. I mean, we went from the mainframe to the PC, then to mobile. But now, in the AI era, the center of gravity has shifted.
It's not the chip on your motherboard anymore.
Not at all. It used to be the discrete chip, the CPU. The Intel era, that was the thing that dictated everything. But today, the core unit is the entire data center AI cluster. It's the whole system.
Which is really the first big step toward this idea of sovereign compute.
It is. And it's forced the big semiconductor players to completely change their game. They can't just sell a component anymore and walk away.
They have to move up the stack.
Exactly. They have to verticalize. Look at Nvidia. I mean, Jensen Huang, he doesn't talk about selling chips. He talks about building supercomputers. He gets that the market isn't buying parts anymore. They're buying fully optimized systems.
Okay, let's use their DGX system as an example. It's got something like 35,000 components. What does that actually give you that a home-built cluster doesn't?
The DGX is the perfect case study. It's not just a box of H100s. It's a completely integrated computer system. Every one of those 35,000 components, the chips, the NVLink networking, the cooling, the software, it's all designed to work together as one organism.
Creating a technical moat.
A huge one, because it's so much harder to compete against a perfectly tuned system than against just a single chip. Anyone trying to replicate that has to deal with what's called the latency gap.
That's the friction between all the different parts.
It's the invisible friction. It's the energy you lose when a component from vendor A tries to talk to a component from vendor B. It translates directly into lost performance, more heat, and just wasted energy.
Which means simply throwing more processors at a problem isn't the answer. And this is where something like Amdahl's law comes in, isn't it?
It becomes the absolute governing law. And for anyone who needs a refresher, Amdahl's law basically says that the speed of your system is always limited by its slowest part.
The bottleneck.
The bottleneck.
Yeah.
You can have the fastest chips in the world, but if your data can't get to them fast enough because your networking is slow, you get diminishing returns.
So adding more and more H100s just stops helping after a certain point.
Precisely. And that forces you up the stack. You have to focus on the whole system, the networking, the memory, the software, to make sure it all operates as a single coherent unit. It's how you keep performance accelerating even when the chips themselves can't physically shrink much more.
Which brings us right back to my VC friend and this renting problem, because this is where the new dividing line is drawn. You either own your stack or you're renting. So for labs like OpenAI or Anthropic, what does that structural disadvantage actually cost them?
It costs them everything. It's two things, really: control and margin. The disadvantage is that you're paying a double layer markup.
Explain that.
Okay, so if you're an AI lab, you're renting your compute time from, say, Microsoft Azure. You're paying Microsoft's markup. But Microsoft, in turn, is buying their hardware from Nvidia, so they've already paid a huge markup on the H100s.
And that's the infamous Nvidia tax. What are we talking about here? Is it a small premium?
Oh, it's market distorting. Nvidia's gross margins on their core AI products have been in the mid to high 70% range, 77%, sometimes higher.
Wow.
So that profit is baked into the price of the chip before it even gets to the cloud provider. Then the cloud provider adds their margin on top. The AI lab at the end of the chain is paying a staggering premium.
So the VC wasn't just paying a bit extra. He was paying rent on rented equipment that had already absorbed a 77% margin. That creates what you call the structural ceiling.
It absolutely does. There was a projection that one major AI lab could be looking at operating losses around $74 billion by 2028. That's not just burning cash. That's a fundamental limit imposed by your business model. You're always reacting. You're dependent on whatever deal Microsoft can cut for you.
But hold on. Google Cloud rents out their own TPUs. Isn't that the same thing?
It's a fair point, but there's a critical difference in the cost structure. Google is probably the most complete vertical integrator out there. They control the hardware, the infrastructure, the models, the apps, everything.
And crucially, they make their own chips.
They make their own tensor processing units, their TPUs, at cost for their own internal use. They completely sidestep that 77% EBITDA margin. This means their internal AI business is just fundamentally structurally cheaper to run than any of their competitors.
And that advantage just compounds over time.
Over millions of training runs, yes, it lets them iterate faster, cheaper. And this brings us to that anecdote about the hardware architect Elias, his idea of architectural honesty.
Right. Tell me more about that.
So his experience really captures this whole shift. He used to be stuck in that latency gap, trying to make software written for one thing run on hardware built for something else. It was just messy, full of friction. Wasted energy. Then he moves to a vertically integrated project, like with the TPU, and suddenly there's this architectural honesty. There are no middlemen, no generic drivers. He could literally trace a single bit of data from the high-level neural network idea all the way down into the specific silicon gates that were designed just for that function.
It's the difference between trying to build something with a random box of Legos versus forging a machine where every single part was designed from one master blueprint.
That's a perfect analogy. And you eliminate all that entropic waste. The machine gains this structural integrity that lets you reach for much bigger goals, like AGI. It's a clean, closed-loop system.
And you can see this in the raw power of Google's TPU progress. I mean, the cadence of their chip development is just staggering.
It's accelerating dramatically. Look at Trillium, the TPU V6. It's got 4.7 times the peak compute of the last generation. But more importantly,
the efficiency.
It's 67% more energy efficient. That's on top of a nearly 5x performance jump. When you scale that to tens of thousands of chips, that's a civilizational level advantage.
And it doesn't even stop there.
No. Then you have Ironwood, the TPU V7. It's a 10x improvement over the V5 generation. These are leaps you just don't see in the commodity hardware world anymore. It proves that these custom architectures are unlocking new types of algorithms, things you literally couldn't run efficiently anywhere else.
But okay, the hardware is just one part of the moat. The software that runs on it is maybe even more important, right?
Arguably, it's the most important defense. We talked about Amdahl's law. You can't just throw hardware at the problem. You need the software to actually use it. And NVIDIA's CUDA is the king here.
It's the programming language for their GPUs.
It's the whole parallel computing platform. It's what lets developers unlock the power of all those thousands of cores on the GPU. And the result is this massive, sticky ecosystem.
If you're an ML engineer, you learn CUDA. It's that simple.
Exactly. The sheer number of libraries, the amount of code out there, that's the real mode. And it's a huge problem for custom chip designers.
Yeah.
AWS, for example, has their Trainium and Inferentia chips, which are great for certain tasks, but they still need compatibility layers to run all the popular CUDA-based libraries that everyone uses. And every layer is more friction, more inefficiency.
So how does Google get around that? They're not using CUDA.
They built their own lock-in. Their ecosystem is centered around TensorFlow and JAX, and their TPUs are co-designed from the ground up to work perfectly with those frameworks. This hardware-software co-optimization gives them performance that you just can't replicate on general-purpose GPUs.
And then they have the ultimate ace in the hole, distribution.
Distribution is the ultimate accelerant. Google can build a new model like Gemini 3 and overnight deploy it to 2 billion users through search and 650 million through the Gemini app.
There's no negotiation, no middleman.
Zero. And they get instant feedback, instant training data. A company like OpenAI has to build that distribution from scratch or pay someone else for it. It's another layer of cost, another layer of friction.
So when you put it all together, this isn't just a friendly competition. It's a new fault line. The owners of the custom silicon can just iterate faster, train cheaper, and deploy bigger.
The bottom line is, this arms race is defined by your cost structure. Owning the factory beats renting it every single time. The winner isn't who has the best model today. It's who can afford to keep shipping the best model every single month without running out of money.
And that runway is determined by the efficiency of your system, which leads us perfectly into the next part of this. Because that structural ceiling, that cost, it's not just an economic concept. It's a physical barrier.
Yeah.
We're moving from market dynamics to pure physics.
We have to ground this in first principles. And the ultimate physical limit on all of this is Landauer's principle from 1961.
Rolf Landauer. And his big idea was that computation isn't just abstract math, it's a physical process.
Exactly. He established that any logically irreversible process, and the simplest example is just erasing a bit of information, has to dissipate a minimum amount of energy as heat.
So information is physical. And when you destroy it, you pay an energy tax. This was a huge deal in physics, right? It helped solve a paradox.
A huge deal. It solved the Maxwell's Demon paradox, which seemed to break the second law of thermodynamics. Landauer showed that for the demon to work, it had to erase information, and that erasure created entropy. It saved the second law. But for us, the key is that it proves our digital bits are governed by the same physical laws as everything else.
Okay, but if there's a theoretical minimum energy cost, the Landauer bound, why are our data centers so incredibly inefficient? Why are we wasting so much energy?
That's the difference between theory and the real world. To hit that Landauer bound, you'd have to do it infinitely slowly, a quasi-static process. In real-world high-speed computing, our erasure processes dissipate. Well, vastly more heat.
So just the speed of it creates friction.
Think of it like brakes on a car. If you apply them slowly over a mile, it's very efficient. If you slam them on, you generate a ton of heat and friction. In computing, the speed and complexity mean heat can't dissipate fast enough. There's friction everywhere.
Which means the VC's expensive server farm isn't just expensive because of the price tag. It's an inefficient physical arrangement that's designed to maximize entropic decay. It's turning friction into literal heat.
Exactly. And that brings us to the only metric that really matters in this new world. FLOPS per joule, floating point operations per joule of energy.
It's the most honest metric. It's how much thinking you get for the energy you spend.
I love that story about Sarah, the thermal engineer, how she sees inefficient patchwork clusters as a thermodynamic crime.
It's such a powerful framing.
It is, because she sees all that wasted energy just bleeding out through abstraction layers, through unoptimized cables. To her, sovereign compute, the fully optimized TPU cluster, is the opposite. It's architectural honesty in the pursuit of physical limits.
And optimizing FLOPS per joule becomes an existential issue when you look at the energy costs of modern AI.
The scale is just mind-boggling. A single query to something like ChatGPT uses almost 10 times the electricity of a normal Google search. It's about 2.9 watt-hours versus 0.3.
And when you're doing trillions of queries,
those tiny fractions of a watt-hour saved by custom silicon and better cooling turn into billions of dollars. It's a massive existential cost advantage. The whole point of vertical integration is to minimize that entropic decay.
This obsession with maximizing computational throughput, with capturing energy, it connects directly to a philosophical movement that's become really visible lately, effective accelerationism, or EA.
Right. Yeah. It's a 21st century techno-optimist ideology. The core belief is that the fastest possible technological progress, especially getting to AGI, is the only way to solve big human problems like poverty, war, disease.
And anything that slows that downregulation safety concerns is seen as a barrier. They call their opponents decels or doomers.
Yes, and the philosophy is explicitly rooted in thermodynamics. The idea is that the universe's purpose is to increase entropy, and life is just a very efficient way to do that. So for them, the goal of civilization is to climb the Kardashev gradient by using more and more energy.
So maximizing FLOPS per joule isn't just good engineering. For them, it's a moral imperative.
It aligns perfectly. AGI is the key to scaling up our energy capture. And their politics reflect that. They're very much against government intervention, usually libertarian-leaning.
But how do they square that with the risks? If they oppose centralized control, how do they plan to mitigate the dangers of superintelligence?
They argue that decentralized free market competition is the best risk mitigation. That having many competing AGIs is safer than having one controlled by a government or a single corporation. They see the AI safety movement with its ethics boards and filters as a kind of thermodynamic absurdity, trying to put the brakes on a system whose whole purpose is to accelerate.
It's important to understand where this comes from, though. It's a mix of a few different Silicon Valley subcultures.
Right. The term itself is a blend of effective altruism and accelerationism. The original accelerationist thinker is the philosopher Nick Land, whose ideas were much more, radical and often dystopian.
His idea was that capitalism should be accelerated to its absolute limit, even if it destroyed existing social structures.
Pretty much. EDEC kind of softens that. It takes the idea of rapid progress, but aims it toward a more positive outcome, scaling the Kardashev gradient for the good of consciousness. It pulls from a whole collection of ideas you sometimes see called TESCREAL.
That's an acronym.
Yeah, for transhumanism, extropianism, singularitarianism, cosmism, rationalism, effective altruism, and long-termism. Basically, it's a whole constellation of progress-focused movements that reject putting limits on technology. EDIC is the thermodynamic flavor of that.
And it's not just an online thing anymore. We've seen very powerful people in tech embrace these ideas.
Absolutely. Major VCs have publicly endorsed it. After the 2024 election, you saw a lot of tech figures advocating for the kind of deregulation that aligns perfectly with XWR principles. In a way, this whole sovereign compute project optimizing silicon for maximum FLOPS per joule is the ultimate engineering expression of that worldview.
So if the thermodynamic imperative is the why, the what is the ability to run these unbelievably massive workloads, the demand for compute in AI is just exponential.
It's relentless. The original AI transformer model from 2017 that took about 7,400 petaflops to train. Compare that to Google's Gemini Ultra. 50 billion petaflops.
And GPT-4o was trained on 13 trillion tokens. It's a scale that demands specialized hardware. You can't do this on a regular CPU.
No way. This is why you need TPUs and Nvidia's tensor cores. They are built for one thing: the massive parallel matrix math that is the engine of deep learning. Without them, none of this would be computationally possible.
Now, historically, most of the money and effort has gone into the training phase. Is that changing?
It is. Right now, maybe 60% of GPU sales are for training, but that's because only a few giant companies are building these foundational models. The number of companies that will use AI, that will integrate it into their products, that's exponentially larger.
So the inference market is set to explode. That's the part where you're actually using the trained model to make a decision or generate a response.
Exactly, and that's the huge long-term driver for sovereign compute, because inference favors hardware that is optimized purely for speed and efficiency. You're doing millions, maybe billions of tiny jobs, and every fraction of a second, every fraction of a joule counts. This is where the sovereign stack's advantage really pays off.
And the ultimate use of all this inference power is not just a better chatbot. It's the rise of autonomous agentic workflows. So what exactly is an agentic system?
It's a system that moves beyond just answering questions. It can autonomously interact with its environment. It perceives what's going on, it makes a decision, and it executes a complex, multi-step task to achieve a wedge. It's the next generation of automation.
But we're not quite there yet. The current tech has some serious limitations.
Big limitations.
Yeah.
Right now, Gen AI chatbots have something like a 15% success rate on complex agentic tasks. They get lost, they can't plan, they can't reason effectively, they lose context.
So to fix that, you don't just need more compute, you need better data, more context.
Exactly. You need highly contextual data. This is where tools like graph databases come in. They help the AI build a knowledge graph to understand how different pieces of information are actually related to each other.
Which is all about achieving what you've called persistent context, getting rid of the forgetful AI.
Yes. Think about that researcher, Kenji, from the anecdote. Before persistent context, he was constantly re-explaining things to his AI assistant, stitching together bits of information. The AI would forget the beginning of a conversation by the end of it.
It's like having a series of short-term memory sessions instead of one continuous line of thought.
Exactly. But now, Kenji's agent can maintain an active memory that spans millions of tokens because the underlying sovereign stack is so efficient. And he said the real breakthrough wasn't just getting faster answers, it was the end of the scarcity of his attention. The AI is like a second brain that never forgets.
How do they actually do that technically? How do you scale that context window without everything grinding to a halt?
One of the big breakthroughs is a technique called long-rope E2. It lets them scale up the context window almost losslessly. They can take a small model and expand its memory from, say, 2,000 tokens to over 128,000.
What's the trick?
It's a kind of mixed training. The model trains on both short context windows to keep its core reasoning sharp, and also on the new long context windows. This dual approach means it doesn't lose its short-term abilities while gaining this incredible long-range accuracy. It can pass tests like the needle in a haystack task with near-perfect accuracy, which was impossible before.
So the efficiency of sovereign compute makes this continuous memory possible, which enables true agentic systems. Which brings us to the biggest idea of all, the planetary nervous system.
This is where you see the ultimate strategic advantage. Look at how Google built Gemini. It's natively multimodal. It can process pixels, audio, sensor data directly. It doesn't have to translate everything into language first.
It bypasses the symbolic bottleneck.
Which goes right back to thermodynamics. The world isn't made of language tokens. It's made of quantum fields and analog signals. Forcing all of that through the tiny filter of language is just fundamentally inefficient.
But a physical necessity to process data natively.
Absolutely. And the vertical integrators are building hardware and models that can understand the world directly at the speed of light.
And their huge distribution networks, search, Android, YouTube, become the sensory organs for this planetary intelligence.
That's it exactly. It's not just a business strategy, it's a biological imperative. Billions of devices acting as the eyes and ears, constantly feeding real-time multimodal data back to the central brain. It's a feedback loop that just reinforces the whole hardware-software flywheel.
So while everyone else is focused on building a better chatbot, the sovereign players are building the infrastructure for a planetary nervous system. That's sovereign compute at scale.
It is.
Okay, so we've covered the economics, the thermodynamics, the agentic future. What's the final consequence of all this? What's the big takeaway?
The takeaway is the compounding chasm. The gap between the sovereign stacks and the renters, it just gets wider exponentially with every hardware cycle. When a new chip offers 10x the performance and is 67% more efficient, the cost disadvantage for renters just becomes insurmountable.
This isn't just competition. You called it technological speciation. One approach is evolving into something fundamentally different, and it's locking all future breakthroughs behind its unique infrastructure.
And that creates a new geopolitical reality. AI companies without their own chips are becoming digital sharecroppers. And we're going to start ranking nations and companies by new metrics: petaflops per capita, joules per inference.
Now, there's a risk of a bubble, right? A lot of money is pouring into GPUs right now. We could see some overcapacity in 2026 or 2027.
There's definitely a risk of near-term volatility, but the long-term structural truth doesn't change.
The long-term demand for inference, for AI embedded in everything, is just going to keep growing, and the companies with the most efficient cost structure will win.
That's the bottom line. The AI arms race is defined by economics and thermodynamics. The winner, no matter what the market does next year, is whoever can afford to keep shipping the best models every month without running out of runway.
So the rise of sovereign compute is really the triumph of engineering, of physical inevitability over market dependency, and, frankly, regulatory caution.
The difference between these two worlds, renting capacity versus manufacturing the physics of intelligence, it's all measured in FLOPS per joule. And that single metric dictates the fundamental limits of what intelligence you can build. The future belongs to those who control the entire stack, from the silicon atom to the planetary nervous system. The verdict is already written in the efficiency of the design.